What is momentum? The momentum of something is basically anything with mass that is also moving has momentum. It's just the product of mass and velocity. That's all it is. However, it is a vector, so it does matter what direction momentum is in, which is, of course, the same as the velocity. So super duper easy to calculate. It's just mass times velocity. Now, the letter for momentum is a P because our M's are already taken, so it's a P. So there you go. So that's the weirdest thing about the equation, but otherwise it's a really nice, easy equation. Also, the units for momentum, they didn't make another fancy unit. They just said, okay, well, it's mass and speed, so we'll just make it kilograms meters per second. But that's basically momentum. Okay, that's it. It's just anything with mass that's moving has momentum. So, because momentum has to do with mass and velocity, then we know momentum changes when either the mass changes or the velocity changes. How do you change velocity? You have to apply a force, right? So there's a force applied to either change the magnitude or the direction of the velocity. And so really momentum, anything with mass that's moving, it's really change in momentum. That's always the more important thing to look at. When things have a change in momentum, we know that there was a force applied. Well, in most cases, sometimes it can gain or lose mass, in which case it's going to lose energy or gain energy or momentum if it loses or gains mass. But we're going to specifically talk about when it changes velocity, we know that there is a force being applied, which changes momentum. And so the change in momentum, delta P, is equal to m times delta V. Of course, delta V would be final velocity minus initial velocity. Okay? Why is this important? Why is it important to look at change in momentum? Well, because we can apply Newton's second law to this. Because, again, Newton's second law is all about net force. And forces are what change velocities. So that rate of change of momentum would be equal to the net force applied to it. Because, of course, we know net force is equal to mass times acceleration. However, acceleration is the change in velocity over time. Oh, my goodness. And then if we plug that in, we have net force equaling mass times the change in velocity. That looks familiar. Looks like something we were just looking at. That was change in momentum, was it not? Right there. So there we go. That's our change in momentum, our delta P, divided by time. And so if I move this this change in time over to the other side of this equation, I get force times change in time is equal to the change in momentum. And this is a very, very, very important thing. It's called impulse. Okay? So a force applied over time will, of course, change something's momentum. Okay? So mathematically, they're the same thing. But why is impulse an important thing? Well, because how you change something's momentum has an effect on it, right? If we change something's velocity by applying a large force over a small amount of time, you can do damage to that thing. But if you slowly change the velocity and slowly make it go faster or something like that, or slower, then you're not applying as much force. You're just applying force over more time. And so that's why impulse is so important. Okay, so first of all, just before I get into here, impulse is newtons times seconds. Momentum is kilograms times meters per second. They're the same thing, because newtons times seconds, well, remember, newtons are kilograms meters per second squared. How do I know that right off the top of my head? Well, I know newtons is because of force, which is mass times acceleration. Oh, look at that. Mass is kilograms, acceleration is meters per second squared. And so if I multiply that by seconds, look what happens to my seconds here. I have seconds squared on the bottom, seconds there. Those cancel out, and I have kilograms times meters per second. So newtons per second and kilograms times meters per second is the exact same thing. It's just newtons or times seconds tells us impulse, and kilograms times meters per second tells us momentum, okay? They are mathematically the same, but conceptually different. So doesn't that sound fun? So why are they conceptually different? Again, impulse is talking more about how much force are you applying over time. So if you increase the time of impact, that will decrease the force because, for example, if our force times time is equal to our change in momentum. Say our change in momentum is, 10. There's a lot of ways to multiply to get 10, right? You can have 10 times 1. You can have 5 times 2. You can have 2 times 5. You can have 1 times 10, right? So applying 10 newtons over 1 second is still going to have a change in momentum of 10 kilograms times meters per second. But we can also apply a 1 Newton force over 10 seconds, which is a very different thing. And so that's why it's really, really important to look at this force times the change in time, because when you increase the time it takes, but you're still not changing this change in momentum, then you have to decrease the force. And that's basically how the concept that any and all safety materials are made based on that whole concept. Okay? Increasing the time of an impact decreases the force of an impact and the resulting acceleration, which is why we have things like airbags. What are airbags trying to do? They're trying to, instead of you impacting your steering wheel, if you crash your car really, 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 really fast, you have very little impact and very little time that you're impacted with your steering wheel, then there's a lot more force there. A thing like an airbag, guess what it does? It decreases the force by increasing the amount of time that you have impact with the steering wheel. Okay? So if your change in momentum is constant, then increasing the time of the impact decreases the force of the impact. Okay, another example of this. Say you're jumping from a really, really high height. What would you like underneath you if you're jumping from a high height? Probably a really big mattress or really one of those big air thingies that you jump onto. Why? Because when you do that, it increases the time. You're still going to have the same change in momentum. You're going to go from moving to not moving once you get to the ground, right? That's the same change in momentum. But the way you change that momentum is very different as if you were to just jump from a high height and just hit the ground. But if you're jumping onto a trampoline or something filled with air or a big squishy mattress, what does that do? Well, the mattress or the air mattress or the whatever increases the time of your impact with the ground and therefore decreases the force that you experience. So this is really, really important. And this is basically just how all safety equipment, this is the principle by which it's designed, is how can we, if something is going to happen, something bad's going to happen, how can we keep people more safe? Well, we can't we can't change the change in momentum, but we can try to decrease the force by increasing the amount of time. Okay? Really, really important concept. If something bounces back, by the way, then the impulse is even greater because not only is it the force then going from downwards to upwards or one way to the other way, there's all the impulse required to bring the object to the stop and then also throw it up again. So anytime something bounces, it has a much larger impulse because there's a much larger force there needed to stop it and throw it back up. Okay? So, again, it's really important that you note that mathematically, impulse is the same as change in momentum. Okay? They're the same number. Okay? So, if you have a 1 kilogram object going from 10 meters per second to 0 meters per second, that is momentum of 10 kilograms meters per second. So your impulse will also be 10 kilograms meters per second. But again, that could mean that you're applying a 1 Newton force over 10 seconds or a 10 Newton force over 1 second, or any kind of mixture of that would get you 10. Okay, so mathematically they're the same. So therefore, if I'm looking for impulse, but I only have information of change in momentum, I can mathematically find the impulse. Absolutely. Okay. Or if I have the force applied over how much time, I can mathematically find the change in momentum. So mathematically they're the same. It's just conceptually that you really need to know that they are different. Okay, so we're always looking at impulse if we're discussing force over time and how much force is being applied over a certain time. Okay, the direction of impulse is equal to the direction of the force on the object in question. Okay, which is not always the same direction as the speed, right, as the velocity. If you're slowing something down, then we know the force is actually in the opposite direction. Okay, if you're speeding something up, then the force is in the same direction. So our direction of impulse is not always the same as the direction of our change in momentum or of our momentum or initial or final. It's always, we're looking at the force, and that's how we get the direction of the impulse. Okay, so let's do an example. I want to know the force exerted on a rocket, given that the propelling gases are expelled at a rate of 1,300 kilograms per second with a speed of 40,000 meters per second at the moment of takeoff. Okay, so we have enough information here to find our change in momentum, which will then help us find impulse, which then, of course, helps us find force. So again, we have force times the change in time is equal to mass times the change in velocity. Which, if I'm looking for force here, I just divide both sides by delta t. But look what I get here, because I'm still given some information in a bit of a weird way. I'm not actually just given the mass, I'm giving how much mass it's dispelling per second. And so technically, we know that we do have this m over delta t here because it's that much mass per second, right? So I could put 1,300 kilograms over 1 second, or I could put 2,600 kilograms over 2 seconds, or so on and so forth. But that's basically giving us our 1,300 kilograms per second. I can multiply that by the change in velocity, which of course the velocity is going from 0 to 40,000 meters per second. Okay, so there we go. We got 1,300 kilograms per second times 40,000 meters per second. Okay, and that technically is our change in, because that would be then minus 0, which is our initial. So I'm just not going to write that. So what do we get for force? We get, well, first of all, we only need 4 significant digits because we have 4 and 5. We take the smallest amount. So in this case, that will be 5.200 times 10 to the 7 newtons, because I only want 4 significant digits. And so therefore, need to write it in scientific notation. And there we go. If you're looking for force in this unit, you're more than likely looking at impulse equaling change in momentum. Okay? There's also a way that you can find impulse if you have a graph. Just like, remember we're going all the way back to physics 20, when you had a force displacement graph. The area between the graph and the x-axis was work, okay? And you can kind of see that because we know, of course, work is applying a force over a certain distance. So say we had a force displacement graph. Then if I took the area between the line and the x-axis, so say that's where it ended, so then I would just find this area here, which is, of course, the area of a triangle. So that's just 1/2 base times height. That's going to be work, okay? So guess what we can do to find impulse if we have a graph? Well, the graph would have to be force because it's applying a force over time. That's what impulse is all about, is how much force is being applied over how much time, okay? And so we can always get impulse by taking the area between the graph and the x-axis of a force time graph. So that'll look something like, well, it'll look pretty much exactly the same as what we had here, except for, or up there, except for instead of a force displacement graph, we'll have a force time graph, okay? And of course, if it looks something like this, then it's another triangle, and then you just calculate the area of that triangle. Okay, so let's try doing that. Obviously, if you don't just have one triangle, if there's a bunch of different shapes, then you divide it into your different shapes. So usually we can divide it into rectangles and triangles and find the areas of those from there. Just like in this graph, because if you can already see, this is a weird trapezoidal figure, so we will break it up into triangles and rectangles. Okay, a force is applied to the right on a scooter. Okay, that's probably going to be important because we do want directions. So if a force is applied to the right, we know our impulse is to the right. Calculate the impulse on the scooter using a graph below. If the scooter has a mass of 80 kilograms and is traveling at an initial velocity of 2.5 meters per second to the left to determine the final velocity. Okay, so we're looking for actually two things. One, we're looking for the impulse, and then two, we're going to look for the final velocity. But let's find the impulse first because it's nice and easy. Okay, so one, finding the impulse. Well, we know that that's just going to be finding area. Okay, and what I'm going to do here is I'm going to make lines there because that's going to help me get my three different areas. So I have a triangle, a rectangle, and another triangle. Okay, so what am I going to do? I'm going to add the areas of all those three guys. So we have the area of section 1/2 base times height. So that has a base of 2 seconds and a height of 100 newtons. We have our second area is just a rectangle, so just base times height. The base goes from 2 to 6, so that's of course 4 seconds. And the height is still 100 newtons. And then we have our third area, which is back to being 2 seconds, because it goes from 6 to 8, and then our height is 100 newtons, okay? And if we find all those and we add them together, you should be able to do that without a calculator. Please, please, please do that without a calculator. 1/2 times 20 is 10, times 100 is 1,000, right? 4 times 100. Or sorry, 1 times 2, I thought that was 20. That's 1 times 2, or 1/2 times 2 is 1. Wow, I'm doing great. Times 100 is 100. 4 times 100 is 400. 1/2 times 2 times 100 is another 100. And we get 600 altogether. Since we're finding impulse, our units should be newtons times seconds. Okay. So there we go. There's our area. And now we want to find the final velocity. Okay, well, good thing that we know the impulse is equal to the change in momentum. And of course, change in momentum is mass times final velocity minus initial velocity. We have the initial velocity and the mass. One really, really important thing, though, remember, the force is being applied to the right. The initial velocity is to the left. Okay, so we are going to have to use some positive and negative numbers. Okay, and I'm going to have to define a direction as positive. So I'm going to go ahead and define right as positive, meaning I know that my impulse, F delta t, is positive, is equal to m times Vf minus Vi. Okay, and here then I know that Vi, my initial velocity, should be negative. Okay, so let's solve for final velocity here. Of course, F delta t is just our impulse. There's no variable for impulse, so we just still always call it F delta t, but we know that is 600 newton seconds. Okay, so if I'm looking for my final velocity, then that is just F delta t over m plus initial velocity. Okay. Again, make sure that initial velocity is a negative 2.5, because it is going to the left, and I said right is positive. And we get for our final velocity 5.0 meters per second. And of course, that is to the right because it's positive. However, I don't necessarily need to say that because I did define right as positive. So since my answer is positive, then that just assumes it's to the right. But you can also say that just in case if you're ever nervous about that. But if you do this right here where you define a positive direction, if my answer is positive, that tells me the direction. Okay? And you don't actually need to have it there. That is it. That's impulse. So again, what's the most important thing about, well, that's actually momentum as well, which is just mv. But really, the important thing is all about impulse and about this guy right here. Increasing the time of impact decreases the force of impact. So now I want you to start looking at in your life everything that is put into measure to keep you safer, and start to realize how much of it is all designed under the premise of this, of trying to increase the time of impact, which will then decrease the force.